Okay, go ahead.
Wonderful. Thank you, Sean. Okay, so last talk of the session, it's my pleasure to introduce Eugene Vinitsky, who is going to give the next talk. Eugene is currently a PhD student in the mechanical engineering department at UC Berkeley. Prior to that, he was at UC Santa Barbara, where he got a master's in physics and did his undergrad also in physics at Caltech. Eugene is very decorated PhD student. He's an NSF fellow, an Eisenhower fellow, and he's also received the ITS Outstanding Graduate Student Award. And for those of you who were in the sessions this morning, he's also one of the Gen 1 Flow contributors. So he has a long history of working with Flow that he co-launched with Kathy Wu, Abudi Kraidi, Feng Yu, and several others. I think today he's going to talk a lot about the test that we run this summer in Nashville, and that's very excited because these results have just been submitted last week. So Eugene, I think the floor is yours.
All right, Alex, thank you for the introduction. And I kind of have a challenge because I have to follow up that talk that we just saw. So this is not going to be too easy for me. I really quickly have just discovered that I do not have the ability to share a screen on Zoom because I have a new laptop. So 2 seconds. I'm good now.
Okay, but it's not on my end. You can share.
I think that's a computer.
I will be back in 2 seconds.
Yeah.
Okay.
I believe
another option will be if not, someone can advance the slides for him if it doesn't work out.
Yeah.
This is the limitation of privacy settings in Apple.
Yeah, exactly. And you need to relaunch Zoom once you edit the privacy setting.
It'll be fine if it comes back.
To allow Zoom to use the
Apologies about that. I can share.
No problem.
Okay. So what I'm going to be talking about is our recent submission, ICRA submission, where we present some of the first preliminary results from the Vander test and talk about how we are trying to learn to smooth traffic directly from human driving data. I just want to point out that this is equal co-authorship work with Nathan Lischlev and Matthew Nice. And I have to pause here that like this work rests on a ton of work done by other people, some of whose names are at the bottom of the slide, and other folks who we just like ran out of space. But this is really a contribution from a large team rather than just the authors listed here. All right, so kind of the goal of the Circles project, and if you've been here, you have probably seen this video a bunch of times, is to smooth traffic waves in real world settings, kind of like the traffic waves shown here on the I-24 in Tennessee. And the result we're going to present in this work is kind of a description of a full sim-to-real pipeline where we train, validate, and eventually deploy controllers that are whose learning is based off collected human trajectories. And I kind of want to motivate this by going through and describing a little bit of what happened in phase 1 of Circles before the testing that we did this year. And so the way we wanted to go about this is that we wanted to learn a controller in simulation and then deploy that controller to the real world with minimal fine tuning. And so since the goal was traffic smoothing, in our simulations, we had to figure out a way to generate the waves on whatever road network we intended to deploy on. And so we wound up with this choice of how do we go about generating the waves? The waves can emerge as instabilities from driving dynamics. They can emerge from instabilities caused by merges or lane changes. They can emerge by enforcing boundary conditions at the ends of the network. And even once we've picked how we generate the waves, there are still a lot of free parameters in the wave behavior. So whatever we are going to deploy on some particular set of waves, and we kind of want our training waves to somewhat match the waves that we're going to encounter. And so we have to answer questions about how fast the waves should travel, what should be the constituent frequencies of those waves. And then, even once we've resolved those issues, we have to, calibrate a bunch of the driving behavior of the agents in our simulator. We have to calibrate the lane changing behavior. We have to calibrate the merging behavior. And so kind of in our first take, what we did was we would pick some wave generating mechanism and rely on existing microsimulation tools and kind of hope that the controller we developed through that process kind of has some desirable properties. And so what we did was we took a chunk of the I-210 in LA. So here we have on the left the Google Maps representation of that. And on the right, we have the reconstruction of that thing in Sumo. And we picked a particular wave generating mechanism. So we said, we're going to place a boundary condition at the end of the network in this ghost cell on the right. And we're going to apply a boundary condition that the exiting vehicles should have some speed. And as the fast entering vehicles come in from this ghost cell on the left, which is another region we didn't just kind of ignore, it's just where vehicles enter from, and they collide with the boundary condition on the right, it's going to generate a wave that travels backwards through the network. And if we look at a video of that, we have these kind of nice looking waves that maybe may look somewhat like what we saw in the earlier videos, and maybe you would think would serve as a good validation mechanism for a wave smoothing controller. So when we did this, and we did some, you can do this by reinforcement learning, you can do this by some other control design mechanism, but what emerges from trying to optimize the energy efficiency of the AVs and the vehicles following behind them in that simulation is this kind of unpleasant, effective energy minimization strategy. So it turns out that in that simulator we constructed, basically the optimal thing to do is drive at 7 meters per second, brake at the last possible second. And this sharply improves the energy efficiency of the cars in that simulator. But it has some undesirable properties, like the controller will not drive faster than 7 meters per second. It will just, if the cars in front of it are going at 10 meters per second, it will go at 7 meters per second. And it had some terribly frightening braking behavior. So this was kind of made me realize that calibration is very, very hard. There are a ton of free parameters to choose from in the how you define the driving behavior of the humans and in how you choose to generate the waves. And then even once you have a calibrated model, there's going to be a lot of difficulties in validating it. There's really sparse data for validating these models. We can have loop detectors on the highway, we can have occasional camera data, but that's only going to let us look at really sparse chunks. And it's going to be hard to validate and confirm that the model we have is the unique model that matches it, instead of one of many models that have totally different behavior that all match this sparse data. And then the last piece of this is this took an absurd amount of engineering effort to try and tune the simulator and even to train agents in it, because once we put all these cars into the simulator, it started to run extremely slowly. So what I'm going to present is kind of a suggestion, or what we did was to kind of skip some of those steps and just think, instead of building a simulator, let's just create a one-lane simulator that is going to replay collected trajectories. So we're going to get some data from driving cars on the roadway. We're going to take those trajectories, directly replay them, and build a simulator out of this. And this has some very obvious pros. So if we're collecting data from the highway that we're going to deploy on, then we're going to get an accurate distribution of wave frequencies and an accurate distribution of highway dynamics. So, the distribution of speeds and how those speeds evolve in time should, given sufficient data, match what we observe on the highway. And then post the collection process, we have this nice data set. We can do a lot of things with it. And there's a minimal engineering relative to trying to build the calibrated simulators that we had before. Some obvious cons, we're not going to have multi-lane interactions. So if there's coordination between the vehicles across lanes, we're going to miss that. And we can't, just by replaying collected trajectories, run lane changing counterfactuals. So we can't ask, okay, if I had driven in this way, what distribution of lane changes would I have observed, and how would that have affected my controller? So collecting the data. So some of the folks listed on the first slide spent a ton of time during COVID just driving around on the I-24, collecting data at a range of different times and different traffic conditions. And so here we have some basically camera footage from one of those drives. And you can see that there's a lot of variability in what's happening. There's a lane that's totally stopped. There's this right lane that's going quite quickly, and fluctuation in the waves. These cars are outfitted with a radar. So on the right, we're going to see some like live results from the radar coming back from cars passing in front of the radar. So we collect the data from the radar. We pull data from the CAN. We interpolate it to match GPS signals at 10 hertz. So our data is going to be, the data set we'll release will be at 10 hertz. We'll downsample for high frequency data, interpolate for low frequency data. And at the end, we have post-processing, we have 60 trajectories on the I-24 going from this along the map indicated here, which corresponds to 9 hours of driving and 800 kilometers of driving data. A nice thing about this data set is when we examine the trajectories that we observe from this, we can see that they're very rich in some sense. So the red curve is velocity. The blue curve is the space gap, so the distance to the lead vehicle. And you can see that there are both huge variations in velocity from across really short time intervals. So you'll go from 18 meters per second to 2 meters per second. And then across longer time ranges, there's also quite large variations in terms of what the kind of average speed of the roadway appears to be. And this might be, you know, kind of complex behavior that would be difficult to get to emerge in the types of simulations we had thought about using before. The data set also contains like a wide range of observed conditions. So it's mostly driving at high speeds, but there is a fairly long tail of low speed trajectories. And so this is just to suggest that this data set that we've collected, you know, does describe a wide range of the conditions that we might observe on the roadway. So now given that data set, we start to construct the simulator. So what we're going to do is we're going to take the ego driving data as a lead trajectory in our simulator. So here the ego is the car driven by our human drivers. We chose to use the ego instead of the lead car because the lead car will occasionally lane change in and out. So there would be kind of discontinuities there. And we'd run into this kind of counterfactual problem where we might have progressed further in space and then a lead vehicle would change in kind of on top of where our car currently is. So we use the ego driving data as the leader trajectory for our autonomous vehicle simulator. This has the problem that we're not going to experience lane changes in the simulator. That's something I'll discuss towards the end of the talk. And so then in our simulator, we arrange a platoon of vehicles as shown in this figure. So the green car is going to be the leader. That's our driving data that we're replaying. The red car is going to be our autonomous vehicle. And then we're going to arrange a platoon of 5 human drivers behind it, driving the IDM model. And one thing I should note is obviously now that we've placed this platoon of human drivers behind it, we're kind of back to the same problem before where we have to calibrate those human driver dynamics. But we found that, you know, generally it didn't matter too much what we set those values to as long as they were string unstable and you know, propagated waves. And then we're going to try to optimize the energy efficiency of this platoon. So our simulator, once we do that, winds up, this is kind of a replay of a trajectory from it. So here the green car is the trajectory leader, the AV is behind it, and you can see that as the trajectory leader, you know, speeds up and slows down, there's kind of like this rippling wave and then the car's behind it. Yeah. So we have our simulator. And now the following question is, how do we build the controller to optimize that our desired objective? So we choose to structure the problem as a partially observed Markov decision process. So this, in particular, the state of our system is going to be things that are, I'm going to say, easily accessible through radar. It was a ton of work on people's parts to get information out of the radar. But once we have that, we're going to use as our state the ego speed, the speed of the leader vehicle, and the gap to the lead vehicle. So this is extremely partially observed. There's all sorts of non-local information that's going to be missing here, like whether a wave is far ahead or things like that. or even what the information about the platoon behind it is. So that platoon information is going to be implicitly involved in the reward function, but not observed. As our action, we're going to use accelerations, not lane changes, just accelerate, decelerate. And then our reward function involved a little bit of construction. So it involves three terms. So there is a constant term that is just there for scale effects. Then our first term is a penalty on energy consumption of the platoon. So here we use an energy function provided by the Circle's energy team, which is a model of the energy consumption of a RAV4. The second term is a penalty on squared accelerations, which we found to encourage kind of smoother driving, which is going to be desirable for placing a human into the car. And then the last term is something that we had to think quite a bit about. So it's a penalty on time headways. So we're going to penalize the learning agent if it gets within a time headway of 1 second or further than 3 seconds. And the key thing is this further than 3 seconds. Sorry, that's a tiny mistake. It's not further than 3 seconds. It's further than 120 meters away. And the reason here is that you can obviously optimize the energy a lot by just coming to a full stop or opening up a huge gap. So we had to pick a penalty on distance that, kind of balanced giving the car the freedom to open up a gap that will allow it to smooth the wave, but also something that won't, heavily decrease the density on the highway. And again, so it's 120 meters penalty, not a 3 second penalty. Though we did observe that once the controller was trained, it never went anywhere near 120 meters. So it was just staying away from the penalization region. So there's just a final note, there's no non-local information and there is going to be no memory. So we're not going to concatenate any of these states together to kind of decrease the partial observability or anything of the sort like that. That's a choice. For the algorithm that we use to build our controller, we use a modified version of proximal policy optimization, which is kind of the RL workhorse in the lab. This is a policy gradient algorithm that does gradient descent on the parameters of the controller within a proximate trust region. And our policy is going to be a 4-layer neural network with TANCH activations. I'm going to really quickly talk about what I meant when I said the proximal policy optimization was modified. So we made a small change to PPO, which is that we provide extra information to the value function. So the value function is a variance reduction mechanism. So it's something you subtract off from the expected reward that reduces the variance of the reward estimators. If you try to estimate this using Bellman backups in this partially observed environment, it does not converge due to partial observability. So we actually add the remaining time in the time horizon as an input to the value function, and then we get convergence. So it's a small technical detail, but it wound up being extremely important to actually training good controllers. Okay, so once we train our controllers, we want to evaluate kind of their performance in terms of the objective we actually cared about, which was the increasing the miles per gallon of the platoon. And so one thing we noticed was that if you kind of look over the whole data set, it's somewhat uninformative. So we tried to break it up into bins. So we binned it into a low speed data set. So speeds less than 18 meters per second and speeds more than 18 meters per second. And we pulled every data point that corresponded to that, computed the miles traveled under those things, and then computed the MPG of those things. And particularly the cutoff at 18 that's where the human driving model went string unstable. So that's why we put the cutoff there. So once we sum up the energies in those bins, we can plot the improvements in miles per gallon in the figure on the right. So I want you to focus for now on the first two columns. So the leftmost one is the low speed data set, so less than 18 meters per second. And the right one is the high speed data set, so more than 18 meters per second. And so each column in the kind of histogram is the vehicle in the following one. So the red one will be the AV. The one to its right will be the first human driver, then the second, third, and the fourth and fifth. So we see that the most miles per gallon increase accrues to the AV, and then the improvement kind of degrades along the platoon, which kind of makes sense. The The driver model that we use is noisy. And so it kind of, your ability to control it kind of degrades as you go further along the platoon. And then inside the column, we plot the absolute magnitude of the performance improvement. We note that here we're not using like the classic train test split of machine learning. We train on all the test data we acquired. We test on all the data that we acquired, and we're going to use the real world as kind of our test and validation of the performance of these controllers. Okay, so a quick bit of controller analysis. So if we roll out the controller on one of the leader trajectories and we plot its velocity and time gap, so the time distance to the leader, we see this kind of interesting emergent behavior. So when there are huge fluctuations in the velocity of the leader, the RL car kind of follows them along. But what the car seems to roughly try to equilibrate around is a headway time gap of approximately 3 seconds. So based on the distribution of waves observed in the data, the controller seems to have learned that the right thing to do is roughly to keep a 3-second time headway, with a slight dependence on what that time headway is on what the speed of traffic is. Okay, so we developed our controller. There have been a lot of talks earlier about the process for actually porting this to the car and validating the controller in simulation before we do it. So I'm going to only touch on that very briefly here. We take our controller, we export it from PyTorch to Onyx, from Onyx to ROS, and then we're going to use a libpanda to actually like send the commands to the vehicle and pull information from the vehicle. And it's kind of visually depicted on the figure on the right. And maybe one important thing to mention is the controller that we output is not safe by default. So we wrap it with a follower stopper controller, which is from prior work from the sort of folks on the Circles team, which should guarantee or increase the safety of the controller. Okay, so then for deploying to the roadway, we had a particular scenario set up, put together by our scenario team. We would have 2 human drivers leading the platoon in blue, and then alternating autonomous human driver, autonomous human driver, so on until the end where we have 2 human drivers again. But one thing to note here is there's these vehicles here in white, which are vehicles that are not part of the platoon. Our vehicles are going to keep some slightly larger gap than humans do. And as a consequence, vehicles are going to be able to lane change in. So there will be an uncertain number of human drivers that have merged into our platoon. And at the bottom here, you can see kind of the platoon arranged at a roundabout before it goes out for tests for the day. So once we deploy to the road, here we have a kind of a screenshot of the deployment with 2 of the AVs marked in green and 2 of the human drivers marked in red. And what you can observe here is that the AVs are keeping kind of a larger gap than the humans appear to, which creates an ample opportunity for cut-ins. And since our simulator did not have cut-ins as part of the training, this is kind of an out of training distribution behavior and kind of a good test of whether the presence of cut-ins is going to sharply affect the performance of our controllers. And so there's really 2 questions we sort of asked here, which is 1, will our controller work? Given that in our simulator, we have a double integrator for the dynamics of the car. And we're missing friction and all sorts of things. Given the differences between the real world and our test simulation, will the controller still work? And then second, given these larger gaps we couldn't test counterfactually at training time, will the cut-ins sharply affect the behavior and possibly, prevent our controller from working by, opening up a gap, a vehicle lane changes in, opening up a gap, a vehicle lane changes in. So kind of inviting things that might induce waves that offset the effect of our controller. So here we have a kind of a playback of the trajectories from one of the recorded lead trajectories from one of our cars. So we went slightly further back in the platoon. So some vehicle that would be affected by this counterfactual lane changing behavior. And then kind of look at whether the controller does something quite similar to what we expected. And what we observe is that even though potentially we could be inviting more cut-ins and cutouts, For a long portion of the trajectory, we're kind of maintaining this 3-second time gap headway with occasional cut-ins that are quickly regulated back to within 2-minute time windows. So this is not all that many cut-ins. And we also here we have two curves. So we have real, so that's the real trajectory of the AV, and then a replay and simulation following the trajectory leader. And we observe that there's quite a close match between the two, suggesting that there isn't this huge gap between the simulator behavior and the real world behavior. Unfortunately, on the test day, there was not actually all that much congestion to smooth. It's kind of an unfortunate event. And we're still processing the data from that real world test. But what I can talk about as a kind of preliminary result is this column here on the right-hand side, which is the test trajectories. So we took the leader trajectories that we observed on that day. We replayed them in our simulator and kind of looked at the MPG that we would have expected to get from those test trajectories. And what we can observe is whether due to gaps in the dynamics or due to now new counterfactual cut-ins, there is a degradation in the MPG improvement, but there's still a very real and significant improvement. And so hopefully as we process the data from the tests, we'll start to see this type of improvement there as well, instead of just in simulation. So future work. So there was no congestion on the test day, on the day that we actually ran this controller. So hopefully we'll rerun our controllers and get some more results. Given the new data that's coming in from the cameras and some of the collected data that we have, we can start to build a simple lane changing model that we can use to add counterfactual lane changes to our simulator and investigate the robustness of our controller with respect to possibly different lane changing models. And then given the collected camera data that is going to start streaming in, we've talked a lot about doing offline reinforcement learning. So just using that data without building a simulator at all and just learning both a value function and a policy directly from that data. Anyways, I think I've just hit the time. So thank you very much for listening. If you have any questions or if there's time for questions, I'd be happy to take them.
Thank you, Eugene. I'll go first, and then I'd love to, if people have questions. So in the training set right now, essentially the leader vehicle trajectories are used without headway information. Would it change if you had a training set where you included lane changes in particular cuts, so where you would train on essentially abrupt changes on headways in addition to actual trajectories?
Yeah, so it definitely would. And we've thought a little bit about it. It's tricky because given the new headway that is experienced in our simulator, it's possible that no car would choose to lane change in there, right? So if for example, if the controller that emerged kept really tight gaps, no vehicle would lane change in there. Possibly there wouldn't even be space to lane change. And so we don't know how to, or in this first pass, we don't have a mechanism for evaluating that counterfactual. You could think of ways to do this. So you could just let the cut-in happen from the data, that the cut-in that did happen, just insert it, right? And if there's an overlap, if the cut-in cuts in on top of your vehicle, you just shoot the lead vehicle forward so that there's a reasonably spaced gap that's still smaller than the gap to the leader used to be. But it's an open question and something we have to work on a little bit for the next test. But given all the data that's coming in the cameras, I think we can build a simplified model that evaluates the probability of a lane change occurring, given the headway to the lead vehicle, and similarly, the probability of a cutout given the headway to the lead vehicle.
Thank you.
I think a quick sort of follow-up on this, right? It's like one thing that we always stress is that there's a chance when we do smoothing that it's not just that the energy impact reduces, but it could also be that the flow becomes more efficient. So we're changing something beyond just making things more energy efficient. The same is probably also true about lane switching itself, right? So enabling lane switching is not intrinsically bad or intrinsically good. It always depends, right? So it's also possible that if you have these AVs driving differently, that it could have consequences that go beyond energy savings or energy efficiency. And we're always concerned about inviting people to overtake us and cut in front of us and do bad stuff, right? But sometimes it's also good to let people lane switch because it makes it more convenient for them to exit, right, and enter and so on. So it's actually not clear cut, right? And it's a very complicated issue at large.
Yeah, that's a good point. I think within the scope of this project, we're often talking about energy, but once we start to get this data in, there's all sorts of questions we can ask.
I had a quick question, Eugene.
Yeah, please.
So I guess I was curious, you acknowledged that sort of like when we're trying to quantify the results for the performance of the controller, it still to some extent has to do with like understanding how a simulated platoon responds behind you, right? Am I understanding that correctly?
That is how we're quantifying it at the moment.
Right.
But obviously the real quantification is what happened on the roadway.
Sure, and that makes sense. I guess I was just wondering, have we thought about whether or not we could use data collected from the automated vehicles that have things like headway measurements to try and understand what we think the most likely car following behavior might be from those instances, and then use that in this context to try and understand what the context would be? I guess I'm just curious, like, how did you arrive at a model to try and quantify the performance?
Yeah, so I mean, we understand that the model that we're using for quantifying performance here is somewhat heuristic, right? Like it's a platoon of 5 vehicles. I mean, one thing that we observe is that it doesn't seem to matter too much what the particular IDM parameters are, and the performance degrades along the platoon, and we kind of know that. So it could be a platoon of 2, could be a platoon of 5. You're still going to get that performance as you move along the platoon, improvements in performance. There is a question to me of whether the humans in our platoon continue to act the same way that like we model them as. Maybe their humans kind of sense there's something odd about the car driving in front of them and begin to drive differently. And so I think pulling the data from that and trying to validate driving models from that would be super interesting. I think at a broad level, like we know that if fluctuations in the cars behind us decrease, energy improves. So as long as kind of the evaluation platform has that feature in it, it kind of does the right thing superficially, but you can make this a lot more refined.
Thanks.
Thank you. Well, thank you so much, Eugene, for the great talk, the latest results and the comments and the answers to the questions. I think this concludes this session. We're now, I think, on a break. Back to you, Amaury, for the scheduling of the last session of the day.
Yeah, thank you all
exactly.
for having me.
Yeah, thanks a lot, Eugene. This was a great talk, and even though I knew already part of it, I was still amazed. So we have now a 15-minute break, and then after we'll have the last session that is chaired by Xiaoqian